Welcome to 32nd annual meeting of AAIC, Bologna, Italy. My name is Dilpreet Bajwa. I am a professor in Department of Mechanical and Industrial Engineering at Montana State University. The title of my presentation is Biobased Plasticizer and Cellulose Nanocrystal Improve Mechanical Properties of Polylactic Acid Composites. The collaborators on this research are Jamila Shojarani, Martin Eicher, and Shrikala Bajwa. The motivation behind this research is to develop a cost-effective, high-performance PLA-based filament for regular and commercial 3D printers. Our aim is to improve ductility and thermal properties of PLA using bio-based materials such as cellulose nanocrystals, bio-based plasticizers, and DDGS. Currently, 3D printer market is around 32.78 billion, and by 2023, it is expected to grow by 25.76% CAGR. And currently, the US has around 37% of the global demand for these polymers. The four most popular polymers currently used as filaments in 3D printers are made from PLA, ABS, polycarbonate, nylon, and they're very expensive. You can see PLA is around $40 to $48 per kg. Same thing with the nylon, $80 to $95 per kg, and polycarbonate is even more expensive. So the three materials we are going to use in this research were: one, polylactic acid. It is a fastest growing biodegradable polymer. It has low toxicity, and it is derived from corn or starch, and it has high strength. However, there are weaknesses with PLA. It has low ductility, low thermal stability, and low impact strength. The second material, distilled dry grains with soluble, is a byproduct of corn to ethanol production. A bushel that is around 25.5 kg gives around 8.3 kilograms of DDGS and 2.7 gallons of ethanol. And the current price of DDGS is around 7 cents per pound. So it's a fairly cheap material. And cellulose nanocrystals derived from cellulose are highly crystalline, have high tensile strength, elastic moduli, and they have a moderate cost. So the objective of this research is to evaluate the influence of bio-based plasticizer, cellulose crystals, and dry distillates on the mechanical property of PLA for 3D printer filaments. The three tasks we took in this project were to identify an effective lubricant that we did in the previous research. We found out two lubricants. One was epoxidized soybean oil, and polyethylene glycol worked the best. And so we picked PEG for this research. The second task was to process PLA, DDGS, CNC, and lubricant-based composites. And the third task was to evaluate the properties of these composites for 3D printers. Again, the materials: polylactic acid, that was a 2002 grade with a molecular weight around 98,000 grams per mole. Cellulose crystals were supplied by the US Forest Product Lab. The dimensions were around 150 nanometer in length and 7 nanometer width, and they were derived from softwood through acid digestion. The plasticizer we used in this project was polyethylene glycol, and obviously another filler, distilled dry grain with solubles. So it's important to look at the composition of DDGS. DDGS has around 10 to 12% fat, which acts like an oil or a plasticizer, 30% fiber, and then we have 35% protein. So it's a good filler for composites. The design of experiment included 5 materials: DDGS, that was a constant at 10%, PEG was constant at 2%, and coupling agent we used around, again, constant at 0.25%. And the two materials that we varied were the CNC. The CNC percentage varied from 0.25% by weight all the way to 1%, and same way the polylactic acid polymer amount varied through these formulations. I want to mention here another thing is that we use two different particle size of DDGS. So the formulation 1, 2, 3 used 60 micrometer DDGS, and the formulation 4 through 6 used 125 micrometer DDGS particles. And the control was no cellulose crystals in the formulation. So the sample preparation methodology included basically taking the materials, blending them together in a container manually, and then drop them into a hopper of a twin screw extruder. So we use twin screw extruder to blend the material. So this is how a filament is coming out of the extruder, and then it is wound on a roller or a spool, and then this spool was used on a 3D printer to print different objects, as well as the 3D printed samples for testing. The characterization of composites was done on both pellets as well as the composite samples. We ran several tests using DMA, universal testing machine we used, and then also we used the DSC and electron microscope, as well as impact tester. So now I'm going to get into results. So the first thing we noticed is that among all this formulation, this is your control where there is no CNC, that as we added CNC, the density of the samples went up. So the 1% samples and another 1% samples showed the density around 1.29, whereas the control, the density was 1.23. The second property we looked at was the storage modulus and the glass transition temperature of composites. And on the bottom is a commercial grade PLA that was used over here. And these are all formulations with plasticizer, CNC, and DDGS. So one thing, if you look at, compare this value, storage modulus, with all other values, you can see as we added DDGS, cellulose crystals, plasticizer, the storage modulus went increase of these composites. But on the other hand, if you look at the glass transition temperature, so the commercial PLA has a glass transition of 69.2, but when we added plasticizer, DDGS, and CNC, the glass transition dropped from 69 to almost 62.91. And part of that is because we are using the plasticizer that has an impact on this. So the next property is Young's modulus of the stiffness. And in this, we can see there is a control with no CNC. And as we add CNC, there is an increase in the Young's modulus. And this is a PLA. So PLA commercial has much lower stiffness, but all other formulations showed a higher stiffness with the CNC and DDGS. And one thing interesting to note is that the samples, composites with the bigger particle size DDGS, showed higher improvement or in the modulus of the samples than the lower particle size. The next property we looked was the tensile strength of the composites. In tensile strength, we did not see any jump or big increase with the addition of cellulose crystals. On the contrary, the tensile strength of the samples came down close to 25% when we added plasticizer and DDGS as well as cellulose crystals into the composites. Now, elongation is an important property because PLA has a very low strain. We noticed that the composite samples without CNC, but DDGS and plasticizer showed the highest elongation, whereas this is the commercial PLA, and all these formulations are somewhere in between. So there were several formulations that showed increased elongation compared to commercial grade PLA. So similarly, the yield at 0.2%, PLA commercial had the highest yield strength at 0.2%, whereas all other formulations showed a little bit lower value. Some were very comparable to the commercial PLA. Another important weakness is impact resistance of polylactic acid polymer. So when we added CNC into it, we can see that the impact resistance of these composites went up. And so this is a 100% commercial PLA. This is without cellulose crystals. So definitely addition of cellulose crystal helps to improve the impact properties. So overall, from this research, we found out that processing CNC in PLA and DDGS is challenging. The major issue is the uniform dispersion of the cellulose crystals in the PLA. The particle size of DDGS had very little effect on the mechanical properties of composites, and we found addition of CNC slightly increased the density of the composites, and also CNC improved the stiffness, Young's modulus, around 13 by 13% in different formulations. We also found that the addition of plasticizer and CNC decreased the tensile strength by almost 24%. The storage modulus increased with the addition of cellulose crystals, DDGS, and the glass transition temperature decreases when we add the plasticizer and the DDGS into PLA. The composites with no CNC showed the highest elongation in terms of strain. As far as also we noticed CNC improved the impact properties of composites. The smaller particles were more effective in improving the impact properties compared to large size particles. Overall, from this study, we found that addition of CNC, plasticizer, and coupling agent can improve the physical and mechanical properties of PLA composites. So here are some of the pictures of 3D printed samples. Here is the tensile bars that we printed using 3D printer. Here is a 3D printer, and then these are some other the objects that we printed using 3D printer. And I want to thank you everyone for listening to my presentation. And I also want to acknowledge North Dakota Corn Council for funding this research. If you have any question, you can contact me. And another important thing I want to share with you is that next year in 2022, AAIC Congress meeting will be in Bozeman, Montana. I welcome each and every one of you to come to Montana and see and attend the conference next year. Again, thank you.